So in the media recently, in particular on the BBC website, there was a lot of interest, a lot of information about a wonderful new type of touchpad technology that is going to be introduced into phones and touchscreens and various other types of household product very soon. And this is something called quantum tunneling, or based around a material called a quantum tunneling composite. To explain it, we obviously have to get back into the wacky world of quantum mechanics and try and understand what the hell quantum tunneling is. What actually is quantum tunneling? It's another one of these bizarre quantum mechanical effects that arise because, although we've got this picture in our heads of small particles, electrons, protons, even atoms, being like this, being like little footballs, in fact, they're not. They have a wave-like characteristic as well. And instead of being found definitively in this position, the particle can be found here, 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 right across a region of space. It doesn't have a fixed location in space. If we've got a football, if we've got it in classical world, and it's coming along and it comes across to a barrier, it bounces off that barrier, unless it's got an incredible amount of energy that it actually passes straight through, bulldozes through the door. Remarkably, with quantum mechanics, because you've got the probability of finding the particle here, 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 and importantly, the other side of this door, because you've got a probability of finding the other side of the door, it means that the particle can actually go right through the door. Even more bizarrely, there's a probability that the particle will be inside the door, inside the barrier.
If you and I were playing hide and seek,
yeah,
there would be a probability that you were hiding in this room, and there would be a probability that you were hiding out there in the corridor.
Yes.
But to get to the corridor, you would have had to get through the door.
Yes. Yeah.
Did the particle have to
No, the quantum mechanically, the particle can literally pass through the door. It doesn't have to open the door, it can get through this barrier. This appears mad, this idea of particles actually passing through solid objects, and it seems like quite an esoteric, weird phenomenon. Turns out that quantum tunneling pops up absolutely everywhere. The reason the sun shines, the fundamental reason the sun shines, is because ultimately particles, protons, tunnel through a barrier. In this case, it's an energy barrier. So what you have are two particles, two positively charged clumps that come together. Now, we know that like charges repel. That repulsion for those protons is very, very large. But because they're not really little balls, because they have a wave-like character, and because the probability of finding them at different positions varies, there is actually a probability that they're found close enough together to trigger that fusion reaction. My computer, the hard disk in my computer, since about 2005, there's been the development of what are called tunneling magnetoresistance hard disks. And these are based fundamentally on the tunneling of electrons through a barrier. Another example is a flash memory. In fact, the way these work, these random access memory devices, is that you store charge, store electronic charge on a computer chip, of course. And the way you actually clear that is that the electrons tunnel through a barrier. So coming back to this technology, this wonderful new touch phone, new touchpad, touch screen technology, how does it work? Well, what we have are nanoparticles, small chunks of matter, which are range between 2 up to 50 nanometers, though those size limits aren't particularly well defined. And the key thing that's happening here is that you're taking those nanoparticles, you're moving them together or moving them apart, and you're changing the rate of tunneling between those two nanoparticles. So let's start off. So the nanoparticles in the film look like this. They're separated by quite a large distance. There's very little probability, if any, for an electron to actually move from particle to particle to particle. So I come in with my thumb, imagine on this scale a very massive thumb comes in, squeezes the polymer, and what happens is that you actually move those particles together. And you're changing the rate of tunneling between those two nanoparticles. So you're changing, what do I mean by that? You're changing the rate at which electrons can move across this gap between the particles. Now this might seem a little strange because when you look at that, first of all, it seems that, well, there's no barrier there, there's just vacuum. In fact, for the electrons, there is a barrier, there's a very strong barrier because you've got a gap, you have got vacuum. It's just like if you took a circuit with a battery and a bulb, you cut the wire in that circuit and you're left with a gap. Electrons won't flow. Classically, electrons won't flow across that gap. But if you make that gap really, 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 really small, down to the nanometer level, then you will actually see electrons flow. When you change the gap between these particles a little bit, it's not like you get a small change in the tunneling probability, you get a huge change in the ability. It turns out that for every angstrom, for every 1/10 of a nanometer, in many cases, you will get a change in the probability of an order of magnitude, of a factor of 10. So for every 1/10 of a nanometer you move these particles apart, you're typically talking about a factor of 10 change in the current between particles. So what we have here is when we bring them together, we see this rapid rise in the tunneling probability. We see this rapid rise in the ability of this film to pass an electric current. And so simply by applying pressure to one of these polymer films, these polymer nanoparticle hybrids, you can change it from an insulator to a metal. And in fact, you can go from a resistance of 10 to the 12, a million ohms, to 1 ohm by applying pressure. And so, of course, that's very easy for an electronic device to pick up that change in resistance. And from that, the key thing is that they are arguing, and quite correctly arguing, that they've moved from a 2-dimensional touchscreen to a 3-dimensional touchscreen because you've now got sensitivity to force in that direction. I guess what really fascinates me, and there are other videos as part of 60 Symbols where I've waffled on about this at length, but what really fascinates me, we've got this incredibly esoteric and incredibly difficult to grasp concept, or concepts related to quantum mechanics, and yet time and time again, despite the fact that there are huge philosophical gaps in our understanding, we still can apply it. And the quantum theory, time and time again, when you apply it to the real world, does a remarkably good job of explaining how nature works.